We're going to focus on two supervised machine learning algorithms in this class, linear regression and k-nearest neighbors. We'll use linear regression to explain some of the ideas behind machine learning, and then in another video, we'll use k-nearest neighbors to get some practice on real data. Machine learning begins with data. Let's explore multiple linear regression from a machine learning viewpoint. In multiple linear regression, which statisticians call multivariate linear regression, there are many predictor variables, call them x1 through xk, and a single response variable, we'll call it y. For instance, we might be trying to predict a home's sale price, y, from the number of bedrooms, x1, the square footage, x2, the number of bathrooms, measured by x3, the distance to the nearest elementary school, measured by x4, etc. The model for multiple linear regression is y equals a constant term, theta naught, plus theta 1 times x1 plus theta 2 times x2, etc., all the way up to theta k times xk, plus some extra error term epsilon. Here, the thetas are parameters. They're numbers that we'll determine from the data, and the epsilon is a noise term which is randomly distributed according to a normal distribution with mean 0 and some unknown variance. Let's try to unpack this definition. If there was just one predictor, x1, then this would look like y equals theta naught plus theta 1 times x1 plus epsilon. And that's just the model for linear regression that we studied before. But this time we've used new names. Instead of using m for the slope, we called it theta 1. And instead of using b for the y-intercept, we called it theta naught. When there are many variables, there's still just a single intercept, or constant term, but there's a different slope for each variable xi. We had formulas to find the parameters theta naught and theta 1 when we did linear regression. There are formulas in this situation too, but I want to focus on the machine learning approach rather than on the details. To fit the model, that is to find the parameters theta I that give us the best predictions for our data, we first define a cost function c. The cost c depends on our choices of the theta i's and on all of our data. For instance, we could define the cost function to be the root mean square error of our regression model. So c is the root mean squared error, and this is the square root of the sum of the squares of the differences between our observed values and the predicted values for our response variable. And here I'm using, in this formula, you can see y and then the superscript I. Here I is not a power of y. I've put it in little brackets to indicate that this is coming from the ith observation. So this is the response variable that we see in the ith observation in our data set. And these numbers, x1 to the I, x2 to the I, these are the predictor variable values for the ith observation in our data set as well. And so this quantity here on the right side of the expression, this quantity is the regression prediction for the y value given that we know the x's. That's given by this formula here, the formula that comes from our model, but we've dropped the noise term. And so we're taking the difference between this predicted value and the actual value, squaring that difference, squaring that error, summing them up, and taking the square root, which is the root mean squared error term. Okay, that's an expression that we've seen before when we were talking about fitting lines of best fit in just a single linear model. We still haven't chosen the parameters theta I, but those are chosen so as to minimize the cost C. This is typically done by applying an optimization algorithm. And so a lot of this and the details are hidden under the hood, so to speak. But one of the most popular optimization algorithms is called gradient descent. Recall that if C is a function of many variables, and in this case, C is a function of these variables or unknowns, theta 0 through theta 1, all the way through theta k, the y's and the x's are actual numbers that we know from our data. So they're not variables, but the thetas are variables. And C is a function of these variables in the thetas. And if that's the case, then you can calculate the gradient. And the gradient of C, evaluated at some values for the thetas, is the vector of partial derivatives of C. So it's a vector. It's got k plus 1 components. The first component is the derivative of C with respect to theta 0. And then the next component is the derivative of C with respect to theta 1, all the way up to the last component, which is the derivative of C with respect to theta k. If we have particular values for the theta i's, then we can substitute these into the gradient to get an actual gradient vector. Okay, this is a vector with numbers as its components, and this vector points in the direction of steepest increase for the function. We don't really want to maximize our cost. We would like to minimize our cost. And so instead of moving in the direction of steepest increase, we'd like to move in the direction of steepest decrease. If we move in the opposite direction to the direction of the gradient vector, if we move in the negative gradient vector direction, then we decrease the cost function the fastest. So gradient descent starts with some random values of the theta i's, and it moves in a small amount in the direction of the negative gradient. So you first calculate the gradient, plug in these theta i's, get a vector, move in the negative direction of the gradient just a little bit, and then stop. We've got new thetas, recompute the gradient value from these new thetas, move in a small direction of the negative gradient, and continue. And this continues until we reach the minimum value for C, where the gradient vector is 0. After applying gradient descent, we found some values for the theta i's in the regression equation. Yeah? And we can use this equation to predict the response variable y, given only the predictor variables x1 through xk. We will probably not spend any time implementing gradient descent, but it's helpful to have a sense of some of the techniques that are used in machine learning. Now, in statistics, we'd be concerned with the variability of our prediction. How much does our prediction depend on the data that we use to generate the prediction? We could use bootstrapping to create a confidence interval for our prediction, but that's not typically done in machine learning. In machine learning, we have another approach to ensure our predictions are reasonable, and I'll be explaining that in the next video.